So, as a recap, yesterday in 12.3a we talked about um, uh, geometric sequences, and geometric sequences are patterns where you're constantly multiplying by the same number, and if you do have a number pattern that exhibits that behavior, say you start with some first term, and then the very next term you're multiplying it by a number, the very next number you're multiplying by the same number, so on and so on and so forth. Those look like commas, they should be ones. There is a predictable formula that describes each individual term, and that is a sub n equals a sub 1 times r to the nth power. Today, we're going to talk about, well, what happens when you add them together. Not surprisingly, just like with arithmetic series, there is a predictable formula, there is a predictable pattern for that as well. Now, just as in that lesson, I'm going to save you or spare you the trouble of deriving it. It's all purely algebra. I think some of you guys might get lost with it. It's the result that matters. But if you are interested, if you are curious, as always, please talk to me and I'll gladly show you where it comes from. But let's talk about the partial sum of a geometric sequence, aka geometric series. So the idea is that for a geometric sequence, the nth partial sum can be found with, or actually it can be the nth partial sum, let's phrase it this way: a sub 1 plus a sub 1 r plus a sub 1 r squared plus a sub 1 r cubed plus dot 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 plus a sub 1 r to the n minus 1 can be found by, and here's the sum formula for a geometric series: S sub n equals the first term times 1 minus r to the n over 1 minus r. Again, if you are interested in knowing where this formula comes from, I'll be glad to show you later. It's just a cool little algebra trick with series. But just like with our arithmetic lesson, it's a pretty straightforward formula to use. If I ever ask you to find a geometric series, that is to say a partial sum of a geometric sequence, it's just figuring out what pieces you have and plugging them in. So for example, if I asked you to find the following sum, and I give you 1 plus 4 plus 16 plus dot 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 plus 4096. Now again, we have to pretend that this isn't 12.3b geometric series. If it doesn't tell you geometric, if it doesn't tell you arithmetic, you have to verify it. But for this particular problem, I hope it's quite obvious, you don't have to do a lot of thinking, that the pattern is geometric because it's times 4 every single time. So here's a times 4, here's a times 4. So I know that my common ratio is 4, and it doesn't take a lot of thinking to see that my first term is 1. The only information I don't have is I don't have the exact number of terms I'm adding up. But just like with last week, just like with arithmetic series, since we verified that it is geometric, since we know this is geometric, we can use a sub n equals a sub 1 r to the n minus 1. We can use this guy to figure out the number of terms we have, because they do give you the very last term, right? They do give you the very last term. So I want to figure out what is that guy's term number. So we use this geometric sequence formula. So the value of 4096 is equal to the first term, which we know as 1, times r, which we know as 4, raised to the n, which we don't know, minus 1 power. This is an exponential equation, so, you know, you're going to have to use logs or use knowledge of powers. So we get 4096 equals 4 to the n minus 1. So solve it however you want. If you want to use logs, be my guess, but you should just know that 4096 is 4 to the 7th power. How do I know that? Well, I know my powers. I have a calculator. So that tells you the n minus 1 is... actually, no, that's not right. It should be 6. Sorry. 4 to the 6th power. Maybe I should do this with the calculator instead of in my head. Yep. So that tells me that n minus 1 is equal to 6, therefore n equals 7. Right, think back to when we solve logs. If the bases are the same, what can I conclude? I can conclude that the exponents are the same, so that's how I came up with the subsequent equation. So all of this tells me that the n number, the number of terms we're dealing with, is 7, so we just go ahead and plug into the sum formula. We're basically done. So what is the sum? S sub 7 is equal, now we're just following the formula that I highlighted above. The first term is 1 times 1 minus r, which we said was 4, raised to the nth power, which we said was 7, all over 1 minus 4. Notice how we have all numbers, so even though it looks crazy complicated with fractions and whatnot, just pop into your calculator. If you do, you're going to get 5,461. So these problems should be a piece of cake. These should be pretty straightforward. Now, just like with arithmetic series, you can do these with sigma notation as well. So if I ask you to find sigma I equals 1 to 6 as 7 times negative 2/3 to the I minus 1, you could do it the old-fashioned way, right? You could plug in a 1, plus plug in a 2, plus plug in a 3, plus so on and so forth. But the idea is that you need to recognize this is geometric. Because it fits that pattern, right? Some number times an r raised to, in this case, it's I minus 1 instead of n minus 1, but it's just a variable. So because I recognize that it's geometric, I don't have to do it one by one by one. We have a formula for it, right? From here, I hope we can read that the first term is 7, the r is negative 2/3, and these two pieces of information together tells me n is 6. So we can actually bypass brute force evaluation of sigmas and then just use the sum formula because we know that this is a sum. So S sub 6 is equal to the first term times 1 minus r raised to the n over 1 minus r. Notice I use parentheses because our r is negative, so you're going to have to be careful with that when you evaluate. So this is, I'm going to go ahead and do this separately. So 1 minus negative 2/3 raised to the 6th power is a positive 64/729, but we still have this minus here, over and 1 plus 2/3. So if you do math, do the arithmetic, do the fraction, so on and so forth, you're going to get 931 over 243. So, simple calculations. But let's just pretend like you forgot this, you didn't recognize it, you didn't notice it. You could still get the same answer by just brute force plug and chug. It'll take a long time, but you'll get the right answer. Now, what makes geometric special from arithmetic is that you can actually find an infinite sum. And that seems sort of counterintuitive. If I add an infinite amount of things, you should blow up to infinity. And that is true for basically any pattern that you can think of. Even if the arithmetic series is very tiny, let's say you were doing, 0.00000001 plus 0.00000002 plus 0.00000003 plus da 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 da. That is a very, very tiny arithmetic series. But because it's infinite, no matter how small you grow, no matter how small you start with, you're eventually going to blow up to really, really big numbers. So it sort of makes sense that when it comes to adding an infinite amount of things, you should always blow up to infinity. Not true for geometric. Because geometric patterns are multiplicative, you can actually force the numbers that you're adding to get smaller and smaller and smaller to zero, to a point where you actually do get a concrete sum. Now this only works if you can force your terms to get smaller. In a geometric sequence, the only way you can force your terms to get smaller and smaller and smaller is if you're multiplying by a number less than 1. Therefore, we have this idea. The sum of an infinite geometric series. This is only true if your common ratio is less than 1 in magnitude. It doesn't matter if it's positive 1 or negative. If the ratio is positive or negative, it just has to be smaller than 1. If that is true, because sometimes it's not always, if your common ratio is less than 1, then the infinite geometric sequence or series So this is the infinite sum of a geometric sequence, which is, again, the first term plus the second term plus the third term plus the fourth term, all the way into infinity, is defined, that is to say, has an answer, and is said to be convergent to, and this is the formula to find it. Sometimes people use s sub infinity to know that's infinite. Some mathematicians just use a regular s without a subscript. So it's not a partial sum, it's the complete sum. It's simply the first term over 1 minus r. So that's the formula you should know. It only works, though, the key here is it only works if the common ratio is less than 1. If the common ratio is bigger than 1 in magnitude, we say the series diverges. That means it goes away from a set number, it blows up to infinity. Although the concept of adding an infinite amount of numbers and still getting an answer may seem trippy, the actual calculations are pretty straightforward. So let's take a look at one last example here. Determine whether the infinite geometric series is convergent. Basically, does it have an answer? And if so, find its sum. So letter A, the first series is 2 plus 2 fifths plus 2 25ths plus 2 1/25ths plus so on and so on and so forth. Part B is 1 plus 7 fifths plus 7 fifths squared plus 7 fifths cubes plus so on and so on and so forth. So again, to do this, you just have to plug into the formula. But the question says, is it possible to get an answer at all? Is it convergent? Remember the test, the thing to look for to see whether or not it's convergent is your R, is your common ratio. If the common ratio is less than 1 in magnitude, so disregard the positive or negative. If it's less than 1, then it's simply convergent, and we can use this formula to find the answer. If it's bigger than 1, then you just say it's divergent, and you're done. So this guy here, letter A, finding the R might be difficult for some people. To me, it's pretty straightforward. But remember, if you can't see what the R is, you just pick two terms that are next to each other. It doesn't matter which two you pick. So I'm just going to randomly pick these two here, just to prove a point. So your R is always the right number divided by the left number. And then you just do math to figure it out that it's 1/5. So the idea is that since R equals 1/5, the absolute value of R, that's important, equals 1/5 is less than 1, the series is convergent. It converges to, and then you just use the formula. S equals the first term, so what was our first term in the sequence? Is 2, over 1 minus the R, which is 1/5. So then you get, what's that, 4/5? So 2 divided by 4/5 is, what is that, 10/4, which is 5/2. So the entire sum is 5/2. Easy peasy. Part B. So what we have 1 plus 7/5 plus 7/5 squared plus 7/5 cubed plus dot 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 dot. I think the R is very obvious, but let's just pretend that it isn't. So pick two terms that are next to each other. We'll just do these two here. R is the right number divided by the left number, which is 7/5. Now this is a problem because 7/5 is 1.2, right? Yeah, 1.2. Or no, 1.4, excuse me, which is bigger than 1. Since the absolute value R, which equals 7/5, is bigger than 1, the series diverges. That's all you got to put, right? If you try to add these up, if you try to add the pattern an infinite amount of times, you're just going to blow up to infinity. There is not a singular answer to this. So that's one neat thing about geometric series, is that they you can actually add an infinite amount of them under certain conditions, and that condition is if your absolute value of R is smaller than 1, right? If the terms are getting smaller and smaller and smaller, you can find the exact answer to an infinite sum. Pretty neat idea.